Hello and welcome to Mathematics with Simon. I'm Simon. My friend Jeremy suggested we explore this Maths Olympiad question and also whether it generalises. So let's take a look at this. X plus y is 6 and xy equals 6. Find x and y. So these are two equations, but they're not both linear. One's linear and one's a product. So if x plus y is 6, then y equals 6 minus x. We substitute that in the product to get x times 6 minus x equals 6. Multiply out the left-hand side, minus x squared plus 6x equals 6. Rearrange that, x squared minus 6x plus 6 equals 0. Use the quadratic formula, x equals 6 plus or minus root 36 minus 24 over 2. 36 minus 24 is 12, and then root 12 is root 4 times root 3. Root 4 is 2, so we can cancel that to the x equals 3 plus or minus root 3. So if x equals 3 plus root 3, then y equals 6 minus x, y equals 6 minus 3 plus root 3, y equals 3 minus root 3. If x equals 3 minus root 3, then y turns out to be 3 plus root 3. So the answer is 3 plus root 3 and 3 minus root 3 in either order, which is fine because the equations had that complete symmetry in the beginning, which is why the solutions come in symmetric pairs. So just to check, x plus y, so let's add 3 minus root 3 and 3 plus root 3, that's 6, and then let's multiply them. It's a difference of two squares, so it's 9 minus 3, which is also 6, so it works. So the first sort of way of generalizing is just to say, well, if x plus y equals 8 and xy equals 8, does the answer have the same form, 4 plus root 4 and 4 minus root 4? And the answer is, well, in that case, x plus y would be 8, but xy would be 16 minus 4, which is 12. It would not be 8, so that doesn't work. How about if x plus y is 4 and xy is 4 rather than 6? Then the solution, if you just generalized kind of naively, you'd say 2 plus root 2 and 2 minus root 2. That's the equivalent of 3 plus root 3 and 3 minus root 3. That would give us x plus y is 4 and xy equals 2. Again, it doesn't work because we don't get xy as 4. In the first case, when we used 8 in place of 6, the product was too big, and in the second case, the product is too small, which sort of shows why 6 is special. What about if x plus y is 0 and xy is 0? Actually, that one works because the solutions are 0 plus root 0 and 0 minus root 0. That works because x plus y is 0 and xy is 0. Everything's 0, but it's probably a little bit of a degenerate case, actually. So we found a second case where it works, but it's degenerate. So let's go super general and just say x plus y is m and xy equals m. What happens then? Well, we solve the equations in the same way we did when we had m as 6. So we go y equals m minus x times m minus x equals m, minus x squared plus mx equals m. Rearrange the quadratic, solve by the formula, you get x equals m plus or minus root m squared minus 4m over 2. There is a solution when m squared minus 4m is greater than or equal to 0. Otherwise, there's no real roots to the stuff under the square root sign. So this is true if m is greater than or equal to 4 or m is less than or equal to 0. So for sort of most numbers in the integers, or indeed in the rationals or the reals, then there is a solution, but there's a short range for which there's no real solution, which is really interesting. No pun intended. You got this, x equals m plus or minus root m squared minus 1. So let's just crunch out some answers. Let's say m is 8. So we tried 4 plus root 4, but that didn't work. So now we see that when we actually crunch it through the formula, we get 4 plus root 8 or 4 minus root 8. So the thing under the square root is actually bigger when m is 8 rather than 6. If m is 4, so m is smaller, then the thing under square root is not 2, it's actually 0. So the answers are 2 and 2, like 2 plus root 0 and 2 minus root 0, because 2 plus 2 is 4 and 2 times 2 is 4. So there's a certain beauty and simplicity to that solution, but it's not the same beauty and simplicity as it is to the other solutions. If m is 0, then it works as we've seen before. We just get 0 plus root 0 over 2 is just 0. But let's take a big number, m is 10. Then you end up with x as 5 plus root 15. So you end up with y as 5 minus root 15. So the thing under the square root is a lot bigger than 5. And as m went up, that effect would only continue. So I think this was the notation Jeremy was using to look at this. Let's say x plus y is 2n and xy equals 2n. So in the case of previously when we said x plus y is 6 and xy equals 6, that would mean n is 3. So the question is, when does x equal n plus root n and y equal n minus root n? Well, for that to happen, xy has to be 2n. So n plus root n times n minus root n is n squared minus n. That's going to equal 2n. Take 2n from both sides. N squared minus 3n equals 0. Factorise. N times n minus 3 is 0, which happens exactly when n is 0 or n is 3. So the first case we explored was n is 3 or m is 6. And then the second case we found by chance twice, which is m is 0. But those are the only two cases when this particularly beautiful and simple solution arises. Thanks for suggesting, Jeremy. I hope you liked the video. Please subscribe and hit the notification bell. I'd love to hear your ideas. And most importantly of all, I hope you enjoy your mathematics. Smiley face.